So we'll write the equations over here. So we have the sum of the forces in the y direction equals the mass times the acceleration. So in the y direction, now we've defined plus y as being downward here. We have T2, we have mg, T2 plus mg. That's in the downward direction. Now in the upward direction, we have T1, and it's the opposite direction, so we actually have to subtract T1. So those are the sum of the forces in the y direction. Plus y here, minus y there. And we know it's equal to the mass times the acceleration. Now we know from the demonstration that the mass was accelerated downward, so we're just going to say mass times acceleration. And so now we have our equation. The sum of the forces in the y direction equals the mass times the acceleration. Now what happened when the string broke? Well, I'm going to just reorganize these terms right here, and I'm going to say that T2 minus T1 plus mass times gravity equals the mass times the acceleration. Well, Pete caused an acceleration in this case the plus y direction. And what happened in the strings? Well, we saw that the string 2, the tension in string 2 broke the actual string. Now, what's going on there? So let's take another look at that. So in my opinion, this problem was kind of tricky, and the reason why is because this difference in tension, T2 and T1, actually is dependent upon this acceleration here. And I'm going to show you that by rearranging this equation to look like this, to say that this T2 minus T1, I'm going to call that a variable, and I'm going to say that that's equal to the mass times the acceleration minus the mass times gravity. Now, in this problem, let's just plug in some numbers so we don't all have variables. And I'm going to say that in the original setup that Pete did in class, here's the fixed frame, here's the string, here's the ball. I don't actually know how heavy that ball was, but let's call this ball 1 kilogram. So if we call that 1 kilogram, we know that I can rewrite this as 1 kilogram times some value of acceleration, which is in meters per second squared, minus 1 kilogram times gravity, and we're just going to call that for now 9 meters per second squared, and we know it's really 9.8 meters per second squared. And we still have this variable T2 minus T1. So now what we have is this equation that shows us that a kilogram meters per second squared, those are the units, minus 10 kilogram meters per second squared is equal to the difference in these tensions, T2 minus T1. Now, I don't know if you can see this by looking at this, but we know, oops, I have a meter squared there, that is goofy. It's actually kilogram meters per second squared, not kilogram meters squared per second squared. What I have here is this term right here, which is kilogram meter per second squared. You probably recognize that as a Newton. So we have a unit of force. So we have that the difference in tensions, also unit of force, is equal to a newtons minus 10 newtons. Okay, so everything works out in terms of the units. So let's continue on with this equation, and let me just show you that this equation looks probably a lot like an equation that you've seen before, T2 minus T1. It's an equation of a line, and in this case the variable that we're looking at is the difference in these two tensions, T2 minus T1, we'll call this the y, and the slope equals mx, right here, mx plus b. And in this case, we can see that the y-intercept, represented by the b term, is equal to negative 10 newtons, and the slope is equal, don't confuse this with the mass, the slope is equal to this, this basically implicit 1 times acceleration. And then the acceleration is our variable here. So here's our acceleration. And then this is our y term right here, the difference in these two. So let's go ahead and plot that. So on an set of axes, if we set this up, we know that here, this would be the y-axis. I can see I'm being quite sloppy here. Here's the x-axis. Let's say each of these boxes is equal to 10, and I'm engineers are a bit persnickety. We're sort of anal retentive, so I want to really make sure that that is on the line here. I'm not doing a great job of this, but in any case, this is supposed to be the y-axis. And let's say this is 5, let's say this is 10. Oops, I don't want that. 10. So I know, this is 0 obviously, so I know that my y-intercept is equal to negative 10 newtons. So let's call this negative 10 here, and the y-axis of course represents this quantity, t2 minus t1. That's the y-axis, and the x-axis represents the acceleration. This is acceleration. And what we see is that the slope is 1, so we know that go over 1 up 1, and we can draw a line. Oh, we can draw a line. Actually, it would be nice to use a different color. Like this. Slope of 1. And so here is the equation of my line, t2 minus t1 equals a minus 10. So this of course extends beyond, extends beyond this. I feel like I'm doing a bad job here, my eyes are getting goofy. So this should be a straight line. I know I've not done a great job of that, but what this tells you now that you look at this line, is that the difference in the tension is a function of the acceleration. So let's say we're at the case where the acceleration is 0. So here is that point right there. So we have the point acceleration 0, and the difference t2 minus t1 is negative 10. So at a equals 0, t2 minus t1 equals negative 10. Or another way of saying that is t2 is equal to t1 minus 10. So in the case where the acceleration is 0, they're at rest, t2 is less than t1. And it could be the case that that you could break t1 first because the tension in t2 is less than t1 when acceleration is 0. But what if we are at a case where the acceleration isn't 0, but the acceleration is actually bigger than, now you can see minus, this is slope of 10, so this is actually an acceleration of 10. We see that at a equals 10, t2 minus t1 is actually equal to 0. Is equal to 0, so the tensions are equal at acceleration equals 10. But what happens when you actually exceed acceleration equals to 10? Well, you can see that when you exceed acceleration equals 10 on this graph, you're actually going upward. And so what you're seeing is that as you exceed 10 meters per second squared, this difference gets larger and larger. Or if we go back to our other picture, as we accelerate, as the acceleration exceeds, as this right here gets bigger than 10 meters per second squared, this tension 2 actually gets bigger than this tension 1. And that's why the string eventually, when you have a very rapid acceleration, the string will break down here.